Good evening, everybody. Let's get started. So let's start off with the announcement. So homework 8 will be due Wednesday, December 2nd. That's posted on the Canvas site. Lab 10 started last week and will be continuing on. So you have until Monday, 12/7 to turn that in. And that will be the last lab. So lab 10 is the last lab. That will be the last use of your lab kit and your analog devices 2, or your analog discovery 2. And then homework 8 is the last homework. So that will be due on 12/2. So my office hours will be right after class today. Come join if you have any questions about anything. And the TAs also have office hours. Those are posted. And as always, unmute if you have any questions during class. I'd be happy to answer. Otherwise, please stay muted so we can keep the background noise low. So what I have up on the screen now is the course roadmap. We are finishing up microcontrollers. We really finished up the material. I'm going to do just an example problem or two at the beginning of today's class. And then we're going to move on to motors and servos. And we're entering this, motors and sensors and electrical applications section of the course. So what I'm going to do now is switch over to the whiteboard. So what I want to do is do a quick example with an LED. I want to make sure that powering an LED using a logic circuit makes sense, because that's a prerequisite for doing some of these microcontroller problems when it says state the logic that you need in order to have an LED lit. So let me just start out with a simple circuit where you have a 5-volt source, a resistor, and a diode, right? So this is an LED. It lights up with several milliamps of current. Equivalently, we have drawn this as without the source, with just a 5-volt node voltage that implies that there is some power supply connected to that node. So that's another way I could draw this circuit. That LED would light up, the resistors limiting the current. So let's talk about, excuse me, how to light an LED with a logical value. What I mean by that is, excuse me, if you have 5 volts or 0 volts node voltage on one side or the other of an LED, how do you get it to light? Let me show you what I mean. If you want this LED on, okay, let me just draw the LED and the resistor like that. What I need is 5 volts with that polarity across this series resistor and diode. And that's how I turn this LED on. So a way I could do that is to have 5 volts node voltage at the top and 0 volts node voltage at the bottom. So if I have a logic level 1, assuming the output of this logic chip can supply enough current to power the LED, if I have a logic level 1 at the top node and a logic level 0 at the bottom node, this LED would light up. If I take the same circuit, and to have this LED be off, right, I want 0 volts across that resistor diode series pair there. So I want this off. I could do this a couple ways. I could have 0 volts node voltage at the top node and 0 volts node voltage at the bottom node. Another way to have this LED off is actually and again, to have plus minus 0 volts across that pair of components. I could have 5 volts node voltage applied at the top, or and 5 volts node voltage applied at the bottom, right? Even though I have 5 volts at this node, this LED is not powered because there's 5 volts at the bottom node. And if you did a KVL around the power supply supplying this voltage, you would see you have 0 volts across that pair of components. Okay, so I just wanted to point that out. When there's a logic circuit that says, what should the values be in order to light the LED or not light the LED, this is something to think about. Okay, any questions on that?
So then what exactly would you write in order to answer that question, like the logic values?
Yeah, I'm going to give you an example problem. It's going to be an example logic problem and microcontroller problem. I'll cover that now.
Okay, great, thank you.
Sure. So let's do a clicker problem. In fact, on just that topic. Let me share a screen here. Okay, so let's suppose you have this circuit right here. So you have on the input side of the AND gate on the left, you have 2 bits, B0 and B1. Those are 2 logical values. And you have resistor and LED. So what values of bits B1 and B2 will cause the LED to emit light? Just take a few seconds and answer that. Okay, take 10 more seconds. Take a guess if you haven't decided already, so you get your clicker credit. Okay, and time. So what you need is 5 volts across this LED and resistor right here. That's what you want. On the right node, you have ground, which is 0 volts. So that means you need a plus 5 volts node voltage at the output of the AND gate. And the only way to get 5 volts, which is a 1, at the output of an AND gate is to have B1 equal to 1, B0 equal to 1. And so that would be D. All right, so that's the kind of problem with logic gates. So how do you light this LED? That's what the question would state. Let's try another one. So here's an OR gate. What values of B1 and B0 will cause the LED to light up? Okay, take 10 more seconds if you haven't answered. Take a guess. We'll talk about this. Okay, so we have plus 5 volts node voltage on the right side of the diode at its anode, and we want 5 volts with this polarity shown here across the diode and resistor. So that means on the left side of that resistor, we need 0 volts. So that is a logical 0. And that means in order to have a 0 at the output of an OR gate, you need 2 zeros at the inputs. Okay, so that's the answer there. Any questions on that? Okay. Well, let's switch over to a problem with a microcontroller in it. So it'll be still a logic problem, but let's introduce a microcontroller. This is the kind of problem you could expect to answer. Okay, so I have this piece of paper here. Let's see if I can make it clearer. That's about as clear as it gets. So here's what you have. You have a microcontroller with output bits, bit 0, 1, 2, 3, all the way up to 7. So you have a 1 byte output here. And you have some gates, logical gates. You have a transistor with a load. And so this is what you want to achieve at the bottom. If LED 1 is on, LED 2 is off, LED 3 is off, and the load is powered. That means there's a current running through that load. What is the value of the byte formed by bits B0 through B7? And then express your answer in hexadecimal. Okay, so what I like to do here is I like to first just identify, well, let's see, LED 1 is on, right? I'll put a check mark there. LED 2 is off, and we're just going to put an X there. LED 3 is off, put an X there. And the load is powered, so I have current running through that load. Let's figure out what the conditions are to make this happen. Okay, so I want LED 1 to be on, so that means I need a logical 0 at the output of that NAND gate, right? So a NAND gate, if I write NAND over here, right, and draw my truth table, I'm gonna do X, Y, and Z, right, just to make it easy to write. All possible combinations of inputs, you could write this down, would be those. Count up in binary from 0. And the NAND gate would have this, right? It's the inverse of the output of an AND gate. So the only way you get a 0 at the output of a NAND gate is to have both inputs equal to 1. Okay, so I'll write those values there. LED 2 is off, so I have 0 volts on the right side of that diode, so I need a 0 here at the bit B5. Okay, so that LED is off. Let's see. Let's go down to the load. The load is on. So if the load is on, that means I have collector current flowing. That means I have base current flowing into that transistor. That means that I need some voltage other than 0 at this logical variable C here. Okay, so that means I need a, maybe 5 volts or a logical value of 1 at the output of that logical multiply. Okay, so logical multiply, if you remember, is an AND gate. Right? So an AND gate only has an output of 1 when both of the inputs are true. So I can figure out B4 and B3 logical values. Okay, let's see. LED 3 is off. Right now, LED 3 is off. So that means I have a 0 at the anode, right? 0 volts at the anode of LED 3. The only way to get a 0 out of an OR gate is to have both inputs at 0. Okay. And so, let's see, that's 0. And then the only way to have a 0 at the output of this OR gate is also 0. So now I know my values. Let's see, B0 is a 0. B1 is a 0. B2 is a 0. B3 is 1. B4 is 1. B5 is 0. B6 is 1. All right. So there I am with my values. The binary value, now I have to express this value in hexadecimal. So let me kind of bring this down to the bottom here. I'm going to divide this 8-bit word into 4-bit words. And let's see, this value here would be 1, 2, 4, 8. 8 base 10, which is equal to 8 base 16. And here I have, let's see, 1 plus 0, 2, 4, 8. I have a 13 base 10. And so let's see, that is a D, as in delta, base 16. And so I put those values together and I get D8 base 16. Okay, so if you program into this microcontroller's port, its 8-bit port, the value, the hex value, D8, then these conditions would happen. LED 1 would be on, LED 2 off, the load would be running, LED 3 would be off. Okay, any kind of, any questions on that type of problem?
I just have a question on LED 1. Why does it need a 0?
To turn on?
Yeah.
Because I need,
Oh, it's the other direction. Yeah. Okay.
yeah, I need 5 volts there for that to turn on.
Got it. That makes more sense.
How do you know that it needs the full 5 volts to turn on?
Versus what?
Well, like if it didn't have 0 there, would it have a 1 voltage there, and then would it have 4 volts?
Yeah, well, if I, so this is assuming, and I would state this in a test problem, but typically we use 5-volt logic. I should put that on here. So
Okay.
so a 0 equals 0 volts, a 1 equals 5 volts. The logical values.
Okay.
Yeah.
Great.
For this.
Thank you.
I guess just to clarify, so you have the 8 base 10 is equal to 8 base 16. That's just converting from the decimal base to the binary base. Is that right?
Yeah, I'm converting first binary to a decimal hex, or a decimal digit actually, and then that's really a hex digit. So hex 8 is equal to decimal 8. So I just did the conversion from binary to hex.
Okay. All right. Thank you.
Sure.
Professor?
Yes.
So, and I think this might just be about the wording of the question. So what does it actually mean when we're asking about the value of the byte? Is that just like how the bits are ordered?
So what I would do is I would give you the order of the bits. So B0 is the least significant bit, B7 is the most significant bit. So I would give you that order. This is typically the way that bits are ordered in a byte. So this, let's see, we're forming a byte out of those bits, and that would be the order. Does that make sense?
Okay, yeah, thank you.
Other questions? Okay. So we're going to switch over now to talking about motors. So finally we get to something mechanical in the course. I like to start by defining terms. So let's define some terms that we're going to use often with motors when talking about motors. So the part that stays still, we're calling the stator. So this would be maybe the case of the motor or the part mounted to something stationary. The part that turns, we're going to call the rotor, and the rotor rotates on a shaft, and it actually rotates on bearings in the stator. And so let's define, starting with some physics, how a motor works. So imagine you have some kind of power supply, battery or a bench power supply, and let's throw a resistor in here for good measure to not short things out. And you have a switch, and you have a couple of rails. So these rails are conducting rails. They're like, wires or pieces of metal. And then you have a sliding bar, which is also a conductor. So that sliding bar is of length L. And if I were to close the switch, then current would flow through the resistor, through the switch, down through this bar, and back to the voltage source. And those rails don't connect together anywhere else. They're left open unless this sliding bar is on the rails. Well, let's take a couple magnets and create a magnetic field into the page, into the screen. So these X's indicate a magnetic field that you may maybe create with a couple magnets on either side of the plane of these rails. What you would find is that when you put current through this sliding bar, right, it can slide freely along those rails, that you will have a force exerted on that sliding bar, and it's equal to IL cross B, right? Go back to physics, and so that's how this magnetic field would apply a force to the current flowing through that sliding bar. And so I is the magnitude of the current, L is the length of that bar, and there's a vector pointing in the direction of the positive current flow, and cross B, B is the strength of the magnetic field. And so you use the right hand rule. If you could imagine, if I could show you my right hand, the current flow cross the magnetic field direction would push that bar to the right. So that bar would slide to the right. So that is a linear machine. It's useful in rotational machines, but there are some examples of linear machines. Probably the most, I would say, dramatic example is a railgun. So this is an example I got off the web of a naval railgun. It actually fires a projectile with no propellant, no explosion, nothing, no expanding gases here. Well, except for what happens when the projectile itself heats up the air. But this is a direct application of IL cross B. You have a big magnetic field. You have a lot of current flowing through a projectile carrier, and that causes a big force. And that big force launches something. So that's an example, probably one of the few examples I can think of a linear machine is a railgun. More commonly, you have rotational machines. So here is an example of a DC motor. So let me show you what's going on here. You have a couple magnets, north pole on the lower right, south pole on the lower left, or upper left of two magnets. And you have a couple wires down here at the lower left where current can flow in and flow out of the circuit. And these two blocks here are called brushes. They rub against something called a commutator, which is split in the middle, so current cannot flow from the left side of this commutator to the right side of this commutator. So with the setup you have here, current would flow through that commutator half, through this loop, around the loop of wire, back to the other half of the commutator, through the brush, back through the wire. And so you can see that, well, if there's a magnetic field here from north to south, and you have I, right, the current I, you're going to get a force IL cross B, right? IL cross B would be this force upward on the south pole side. Then as you look at the other side, right, the north pole side here, IL cross B, because current's going in the other direction, causes a downward force instead of an upward force. So that would tend to turn this loop of wire. So this loop of wire can rotate on those brushes. And so imagine it rotates 180 degrees and you have the same case. You have a force up on the left, a force down on the right, and this machine keeps turning. This is I call it a cartoon because, well, when this commutator turns 90 degrees, you're going to be shorting between those two brushes. That's probably not such a good thing. You probably want a lot, many more segments of this commutator compared to the brush size so that you don't short out across the brushes. But this does explain the principle behind how to take that linear force and convert it into rotational force. Here's a more realistic example of a DC motor, an actual DC motor, right? So what you see are the two brushes which rub up against this commutator, and this commutator split into several bars. It looks like probably 8 bars here. And so that keeps brushes from shorting out across adjacent bars. And what you would have is you would have wires, coils of wire, coming off one bar, wrapping around this armature probably several times, and coming to the opposite bar. So you have all of these coils of wire that have current through them, and then you get an IL cross B actually acting on each turn of the coil. And then as that armature spins, one or two of these commutator bars are energized, so you get one or two of those coils energized to cause force to make that motor spin. A good example of a motor from the side view is this. So this shows the case where the field, the magnetic field, is actually not caused by permanent magnets, but rather an electromagnet. So if you take a coil of wire, wrap it around a nail, and run current through it, you could see you could pick up pieces of metal, you create a magnetic field. That's the same principle that is used here. You wrap a coil of wire around part of the stator, and so the coil is going in at the current in the coil is going in at the top, wrapping around the back, coming out at the bottom, with several wraps of that coil, and it's creating a magnetic field. And so you'd have a north pole on this side. On the opposite side of the stator, you'd have current going in the top, coming out the bottom, but on the right side of this coil, you get a south pole. So now you can imagine that magnetic field is created by those two field windings, and then you have commutator bars conducting current into one side on the right side, out of the left side here, as shown here in this picture, and so you get some torque, and this motor spins. So that is the principle behind how you make motors work with either permanent magnets or electromagnets creating the magnetic field. There are many different types of motors. We're going to talk about a couple types. So you have an AC induction motor, a synchronous motor, shunt connected or permanent magnet DC motor, series connected DC motor. Typically, well, when you go buy one from a store for a cheap motor for a project, it's likely a permanent magnet DC motor. We used to use these in lab. They have this torque versus speed characteristic that I want to talk about. So this is a common DC motor. On the vertical axis is torque. On the horizontal axis is speed. So you could think of that in maybe units of RPM, right? Revolutions per minute. So a common DC motor has this sort of characteristic where you operate the motor And if you apply no load to that motor, you will be running that motor the fastest. It will be operating at its no load speed. So you're not applying any external torque. That's as fast as the motor will spin. And then as you apply torque, right, you're loading that motor, you're doing something with it, turning a fan or driving a wheel. As you apply more torque, the motor slows down. And eventually you'll get to the point where you stop this motor, and that's called the stall torque. And the characteristic is roughly linear like that. So we'll talk later about, well, how do you, let's suppose I have a varying torque and I want to maintain a constant speed. Well, there are ways to do that, but it's doing it electronically instead of just relying on providing a constant voltage source to this motor and expecting it to maintain a constant speed. I'll talk about speed control in a few slides. Another kind of motor we're going to talk about is the stepper motor. It is a synchronous motor. A synchronous motor's torque versus RPM characteristic looks like this. It's just a straight line. So within the normal operating range of this motor, it maintains a constant speed. In fact, you're going to see that you can use a microcontroller or other digital circuit to precisely control the speed and position of a stepper motor. So the point here is that the speed is independent of load, as long as you're within the specified load of the motor, but you can make that motor turn at a constant speed and actually maintain a certain angle with an external controller. So we'll talk about that. So how to control DC motor speed? Well, what you can do is you can vary the voltage across the motor in order to control its speed. And one way that you've actually learned already, I think you've done it in 2 labs so far, is controlling voltage with pulse width modulation. So you can use that when applied to a motor. It's pretty common to use this technique, PWM, for a DC motor to control speed. What you do is you pulse the motor with varying pulse widths in order to control the average power delivered to the DC motor. Okay, so you're turning the supply voltage on and off, let's say 5 volts and 0 volts, 5 volts and 0, or 12 volts, whatever the motor's rated voltage is. You can turn it on and off, and I'll show you an example of that. And the duty cycle, as we've talked about, is the time that the power is on divided by the cycle, the period of the cycle. Okay, so that's what duty cycle is, just like we defined in lab. We're going to use that duty cycle to control the amount of power delivered to the motor and the speed of the motor. So if you want the motor to turn its fastest speed, you power it up. Let's say it's a 5-volt motor. You turn it on and you let it run, and that's as fast as that motor can run. Make sure I've got my chat on here. And so let's look at slowing this motor down. Okay, so you can slow the motor down by reducing the duty cycle, and that reduces the amount of power delivered to that motor, right? So you have an average voltage effectively applied to this motor. That's what that red line there is. So if you have an 80% duty cycle, you're applying 80% average voltage to this motor, and it's going to slow down. If you want to slow that motor down even further, apply a 20% duty cycle. So you're not changing the frequency, you're not changing the voltage from the power supply, you're just turning on and off that voltage, maybe through a transistor or other driver in order to slow that motor down. It's a lot easier to turn a power supply on and off than it is to adjust its voltage efficiently anyway. And then so you use different pulse widths, but the same frequency. In fact, if you some drills use pulse width modulation, and if you take a like a battery-powered handheld drill, and you just barely squeeze the trigger so that you can. So the motor's not yet turning; it's not making a lot of noise, but you can start to hear the frequency of the pulse width modulation, and you can tell that it's using PWM. And then to stop the motor, of course, you can use a 0% duty cycle, just like when you were flashing your LED or turning it off. And so you can adjust from full speed to no speed, and you could actually include this in an active control system that would feed a speed back, in other words, measure the speed back to a controller, and that way it would maintain a constant speed if you want that. Now, we talked about pulse width modulation. If there's an average voltage output, there needs to be some kind of low pass filter. In the case of the flashing LED, it was your eyes. Your eyes cannot react that fast. They have a low pass response to flashing light. So your eyes were doing the averaging. And you could even see in your lab when you flash your infrared emitter and you look at the voltage out of the detector, you know, there's flashing going on, but if you replace that emitter with an LED, you wouldn't be able to see the flashing above, you know, maybe 30 or 40 hertz. So here, in this case, it's the mass of the rotor that is acting as that low pass filter. So as you apply pulses, the rotor speeds up, but as the pulse goes low, the rotor does start to slow down a little bit, but before it can apparently slow down, it's hit with another voltage on pulse. So it has the effect of being a low pass filter. Someone asked in the chat, how do brushless DC motors work? Well, so what you can do is you can create, and you'll see a stepper motor in a minute. It actually does not have brushes, and you can create a brushless motor a couple ways. You can create a magnetic field, and you can have a permanent magnet on the rotor, and you can move the magnetic field. You can energize different coils around the outside of a motor and make the rotor turn. And there doesn't need to be any current going through the rotor, so you don't need brushes. Okay, that was speed control. Let's talk about direction control. So how do you control the direction of a DC motor? You want to build a car, you want it to go in reverse. Well, here's how you can do that. It's a configuration called an H-bridge. So here I have a motor in the center surrounded by switches. So if there's a 5-volt node voltage at the top provided by a power supply, ground is at the bottom. So current is trying to flow from top to bottom in this diagram here. And the switches are either allowing the current to flow or stopping the current. Let's define for this particular motor that if current is going from left to right through this motor, we're going to call that the forward direction of the motor. If you reverse the direction of current through a motor, its shaft turns the opposite direction for DC motors. So let's define current going from right to left through this motor as having the reverse direction effect of this motor. Okay, so what I would like to do is I would like to have current flow down from the source through the motor from left to right and down to ground. So I can do that like this. I close switch A, I close switch D, and that lets me have current flowing from left to right through that motor. Okay, and so we can build a table to do this. This table will be useful when I talk about using transistors to do this. So I want, in order for the direction to be forward, close A, open B, open C, close D. To spin the motor in the opposite direction, well, do the opposite. Close switch C and close switch B, and you get current flowing down from the source through the motor in the opposite direction. Okay, so here's the table. You reverse the state of the switches, and you get the reverse direction happening. Okay, so you can control the direction or stop the motor with the H-bridge switch states. In fact, you can combine pulse width modulation and the H-bridge, and then you could control direction and speed. I could actually open up, let's say in this case that I have on the screen, if I open and close switch D or switch B or both, or I turn the power supply on and off, I could pulse width modulate the current through this motor, and that would let me control the speed. And then you use the state of the switches also to control the direction. Okay. Any questions on that?
Yeah. So for stopping the motor, would you just apply a reverse current to the way in which the motor is rotating to stop it, or do you do it otherwise?
One thing you could do, you could just open up all the switches, and that would be a free run stop of the motor, right? And you could also open switch B close switch B and switch D, and open switch C, and that would cause 0 volts across the motor. Okay, so that would be a fast stop. You'll see some of these states listed on a data sheet that I'm going to show you on what it means to stop the motor. But simply, you could just open up all the switches and the motor will stop. Make sense?
So are you relying on friction to stop the motor?
Yeah, yeah. But you could also, if you apply 0 volts, the motor, then you are inducing a magnetic field in the motor, right? You have a magnet going through a magnetic field, and it's going to be more of a fast stop. It's going to dissipate its energy elsewhere in the circuit. If you allow power, basically what you're doing when you're depowering a motor, I'll say, and you want to stop it, one way you can stop it is actually to make that rotational energy go somewhere else and be dissipated somewhere else. And so your motor becomes a generator. And so if you short out the B and D, the power is going to be delivered to the wire or somewhere else in the circuit.
Okay, thanks.
Mm-hmm. Okay, so let's take a look at how to do this with transistors. Okay, so that was a very mechanical way, I'll say, by using switches in order to control the current through a motor. What you would likely do is use some electronics means like a set of transistors, or maybe a specialized chip that would do that. But let's draw out this H-bridge in a way where you could just use transistors. So I'm going to draw a different kind of transistor here in the upper left and the upper right. I'll talk about those in a minute. Okay, so let's apply 5 volts at the top, just like we did before. Ground at the bottom. But what I've done is I have used NPN transistors at the bottom, and I'm using what's called PNP transistors at the top. So these are NPN at the bottom. There's a little way to remember NPN versus PNP. the arrow of an NPN is not pointing in, NPN, not pointing in. So that's how you can remember the difference. The PNP has the arrow pointing in. It's still on the emitter, but the arrow is pointing in. So let me define some logic variables here. Let's call this logic A, logic B. So 5 volts or 0 volts, C and D. Let's define the forward direction current going that way. And let's define in the same way we did before. This is the reverse current direction through the motor.
Professor?
Yes.
So practically, what is the difference between NPN and PNP if like it's still going ultimately in the same direction, right?
Well, the current's actually going, so the difference between an NPN and a PNP physically is an NPN has the N region and P regions like arranged like this. So this would be the collector base emitter, right? A PNP, well, has P and P like that, collector base emitter. And all that means is that take all of the currents and all of the voltages and reverse directions and polarities. Okay, so instead of current flowing into the collector, right, for an NPN, currents flowing out of the collector for a PNP. So the currents get reversed, the voltages get reversed, everything's reversed. But other than that, you treat them in the same way for analysis purposes that you did with an NPN transistor. Okay. So what this lets you do, and I'll show you this in a minute, this lets you reference the logical voltage here, right? This value A, whatever voltage shows up there, you're going to compare it to 5 volts instead of 0 volts in order to control the collector current. I'll show you what I mean.
Okay, so for the top one, for the PNP one, the collector is the bottom node.
Right.
Okay.
The arrow is always on the emitter.
Oh, okay, gotcha.
Mhm.
Thank
Sure. Okay. Okay. So let's start here. Let's create a table. So here's the direction, and I have 4 logical variables. And those logical variables, they're 0 volts or 5 volts, corresponding to the zeros and ones. But for the forward direction, okay, what do I need? I need current flowing down through this transistor, down through this transistor, right? And down to ground. So that's what I want. So let's talk about how to get current to flow at let's call it transistor D down here. Well, we know how to do that, right? If you apply 5 volts to D, you will get base current flowing from that node down to ground. Let's assume this resistor is designed so that that transistor saturates. So I've saturated that transistor. It's essentially a switch that is closed, connecting the right side of the motor to ground. Okay, so that's, I want D to be a value of 1. Let's go over to B. I want this to be an open switch. If you remember from the slide, I don't want any current flowing through this transistor here. So I want, so no current flowing there. I want B to be a logical 0. That transistor is in cutoff. It is an open switch. Now let's go up to transistor A. I want that transistor to be saturated. I want that to be a switch that is closed and allows the current to flow. So what I need to do is I need to have base current flow, right, in order to saturate that transistor. This is a PNP transistor, so base current flows that way from right to left through that resistor connected to A, right? And collector current flows out of the collector instead of into the collector. So what I need is I need a voltage applied, VBE, right? VBE is the voltage between base and emitter. I need to apply a voltage that makes that, well, 0.7 for a silicon transistor so that current can flow through the base and cause collector current to flow. Okay, so what I actually need to do here, since I have 5 volts at the emitter node, I want 0 volts at this node A here, because this is a diode, right? The emitter to base junction is a diode, and I want current to flow. So I need, right, just like the LED circuit we looked at earlier today, I need 5 volts node voltage on one side, 0 volts on the other. That will cause base current to flow. That will saturate this transistor, and collector current flows. So A needs to be a 0 for that transistor to be on. C over here, we want this transistor to be off or in cutoff. And so I want this voltage here to be 0 volts, right? I want that base to emitter junction to be 0 volts. And so how do I do that? I apply 5 volts at C. So I have 5 volts on one side of this resistor diode combination, 5 volts on the other side, 0 volts across. That transistor is in cutoff. Okay. So these logical values are how you control these 4 transistors to make that motor turn forward. Okay. All right. So I've gone over time here, and what I'll do is, if you have any questions about this, let's talk about this during office hours or at the beginning of next class. We'll continue on with the DC motors talk. Okay, so don't forget you have homework 8 due on Wednesday, December 2nd. Lab 10 is due Monday, December 7th. Thanks for joining class. I hope it's working out well. I hope these last few classes will go well for you. Let me know if anything isn't, and I will try to fix it if I can. So have a good night. If you choose to join office hours, I'd love to see you. If not, I'll see you next time. Have a good night.